begin.
Hi Jeff, how are you doing? I'm Declan Mulhall from the University of Scranton, and I'm going to show you my me scattering setup that I had the fourth year students in Electromagnetics Design Lab perform. And I'm going to have the second year, the sophomore modern physics students do it in September. Okay, it's a very simple setup. I've got a couple of extra bits and pieces, but you don't need these. You could do this whole thing with a laser pointer if you wanted. This is a laser that I found in a closet. And this are two mirrors where we can adjust it so we can get a nice parallel beam. You don't need that, of course, that's just being fancy. I'm going to turn on the laser. Now, I prepared the beam by, if you can see, there's the beam profile. Okay, Michael, can you show the beam? Can you show the beam right there? Okay, so the beam is there, right? But I use these. There's a Polaroid over here, Michael. There's a Polaroid, and then there's an aperture here and an aperture here. They were important to clean the beam. You had to have it nice and clean, otherwise you'll get all kinds of crap. You won't have a nice profile for the beam. This is an optical chopper. I'm going to turn it on, and now I'm going to run it. So this is going to chop the beam. It's going to make it go on. I don't know how much, Jeff, I don't know how much you know about this kind of stuff, but so this could be very pedantic. But this is chopping the beam on and off. You can set whatever frequency you want. We've got it set to 511 hertz. So the light, after this wheel, the light turns on and off 507 times a second. Or 511 times a second. Now we've got our sample. Our sample looks like this. This is kind of chintzy, but I mean, who cares? It works. I just blacked off tape here because if you, Michael, can you come down here and we'll show Jeff the beam going inside. Can you see the beam going inside through the water? That's the level of, that's the concentration you need. You can have the students do complex calculations to find out how much of the sample you need to put into the water, but it turns out you need enough to see the beam, not too bright and not too faint, so you can kind of make it up as you go along. I put on the black tape so I didn't see the side of the beam. I just want to see what's forward scattered, not refracted out the side. Okay, I'm now going to turn off the lights and show you what the beam looks like when it comes through the sample. Michael, can you go up that side and show Jeff this picture? Do you see the, can you see the lines there?
Yeah.
You can?
Yes.
So okay, Jeff, you see these circles? They're the diffraction patterns from, actually I should shake it up, hold on. They're the diffraction patterns from the, there's the diffraction pattern from the sample. That's lovely. We're going to measure the angles at which they occur. Okay. We're going to measure the angles at which they occur by moving this detector through whatever angle we need. The way I measure angles is I got a bit of scotch tape through a hole in a meter stick, and there's a line on the scotch tape, or a reticule I think you'd call it if you wanted to be fancy, over a protractor. You can make it up as you go along. I actually, what I also did was I bought an expensive rheostat to hook up to this, so you could have voltage as a function of angle, but I didn't get to hook it up. This detector, this is a $13 detector that I got from Tor Labs. For all this equipment that we used, I can email you a shopping list if you'd like that. The output from the detector goes here into the lock-in amplifier. A reference from the optical chopper goes into the lock-in amplifier. And now the lock-in amplifier is now this needle on the lock-in amplifier is our well, what did I just do? The needle on the lock-in amplifier. This is our detector. Oh, I didn't turn it on. Sorry, got to turn on the lock-in. Okay. So now, when this settles down, I'm going to show you. Well, Michael, if you stand back, can you can we see the needle? Okay, can you bring it in? I'm going to show you. I'm going to make the needle move. The needle has moved up. Okay, it's down. And now it's paused and went up again. So I'm going to increase the sensitivity. There was a peak. Okay, so okay, hold on. I'm increasing the angle. Okay, hold on a second. Sorry. Oh Jesus, hold on. Everything's wrong here. Okay. Let's just do this real quick. Okay, I'm increasing the angle. The needle's dropping, as it should. Then it should increase again. Oh, there was a little bit of an increase. Okay, hold on. We're going to sit on a peak here. Okay, so I'm increasing the angle. The needle is dropping. And now it went up again. Now it drops. No pauses. Now it went up again. And now it dropped. Okay, Michael, can you stand back and show, we'll show Jeff what I actually did with the detector to make the needle do all that stuff. I started off here, and I said the needle is dropping. Now it went up, and it dropped. It went up, and it dropped. That means that at here and here, there's two angles for peaks. The students will get that data from the local amplifier. This is just a gauge. You actually get the output from here. You just hook it into a voltmeter, and it'll give you a multiplier between 0 and 1 for the sensitivity scale. So it's pretty straightforward. Now you wouldn't even have to, if you turn, look, we've got the room lights on. You wouldn't even have to have a local amplifier if you just turned the room lights off and got up a little closer. So I don't know if you have one or if you don't have one. Okay, so that's it. Goodbye.